This is the introductory lecture for my course on history and applications of calculus. So all I'm going to do is going to be a rather short lecture. I just want to quickly tell you what my goals are and explain how I recommend that you take the course. And then at the end I'm going to just show you how to use LaTeX using overleaf if you're going to attempt the homeworks, which I strongly encourage, and type them in using LaTeX. That's a great experience. So I'm going to just give you a very quick guided tour of how to do that. So the idea of this course is kind of a second course in calculus. So all I'm going to assume is that you've seen the first course in single variable calculus, which is probably AP Calc, the more advanced AP Calc with some trigonometry in it, which you've taken in high school. Perhaps that's a first year college class. I'm going to assume you're rather good at math, so I'm going to be doing quite sophisticated things with trigonometry and integrals and differentiation and so on, but I'm not assuming that you know anything more than the standard topics from that single variable calculus class. So if you're taking the course, it's a 10-week course, and each week I'm going to have 3 lectures on YouTube. And really, I encourage you to just work through it at that pace. Aim to spend 10 weeks just slowly going through this material, watching the lectures, thinking about the lectures, kind of rewinding them, understanding things, working things out, maybe looking things up on Google if there's things you don't get in the lectures. Just systematically work through the lectures. Then each week there's going to be reading, which will be mainly kind of historical reading. So I encourage you to do that reading. Perhaps after you've watched the lectures, do the reading. And then each week there'll be a bunch of homework problems. There won't be a vast number of homework problems. I'm trying to give 3 or 4 interesting homework problems that might be quite challenging, but which you can work on, and by solving, it'll keep you on top of the content for the week. And then the final thing I really encourage is that once you've solved the homework problems, I really encourage you to typeset them using LaTeX, which is a special language for typesetting mathematics. So I'll talk about that a little bit more at the end. But that way, through this course, you'll brush up on your calculus. You'll see lots of the cool applications of calculus, which is really why it was invented. And you'll experience reading mathematics by yourself, and you'll learn some of the history. And finally, you'll experience writing mathematics using LaTeX, which is a very useful thing to be able to do. So let me just tell you very quickly what the topics are that I'm envisaging for the 10 weeks of class. So I'm going to start out in the first week with a review of differentiation, of differential equations, and of integration, and then we'll talk about the fundamental theorem of calculus. So, of course, in reviewing differentiation, I'm going to do lots of trig, because we really need loads of trigonometry. In all those physical applications of calculus, trigonometry is kind of essential. So I'll spend quite a lot of time reviewing trigonometry. Of course, differential equations is basically laws of motion, why it was all invented in the first place, to give the mathematics that can model the physical world that we live in. Integration, I'm sure you've done quite a lot of that stuff, areas and volumes. And then finally, the fundamental theorem of calculus. That was the real breakthrough, which I think was really the birth of calculus when the fundamental theorem of calculus was observed. So this is the theorem which connects integration to differentiation. So that's the first week, and then in the second week, I'm going to start talking more about conic sections, ellipses, parabolas, hyperbolas, and I'll talk about them in Cartesian and polar coordinates. And really, I'm going to do quite a lot of teaching of this material, because although you probably get a glimpse of these things in your first course in calculus, somehow it never quite goes far enough. So it's always frustrating in that first course. You never quite get far enough into a topic to do interesting and cool things with it. So I'll tell you some nice things about parabolas and ellipses and hyperbolas. I will use polar coordinates, which is really more natural. I'll also talk a little bit about parametric equations. There's another topic that you probably touch upon, but I want to give more examples like cycloids and cardioids and other such things. So really, I'm in those 2 weeks, I'm kind of teaching you the tools of single variable calculus, maybe going a little bit further than you would have seen in that first course in calculus, because we need to get our skills to the point that we can understand some of the later applications. So all that stuff about conic sections and parametric equations is building up to week 4, when I'm going to talk about Kepler's laws of planetary motion and I'll explain Newton's proof of Kepler's laws. So that's kind of one of the real astonishing achievements of humanity, I think, is Newton's formulation of the laws of motion and the law of gravity, and setting up enough of the theory of calculus and differential equations that he could give a completely rigorous mathematical proof of Kepler's observed laws of planetary motion. So that's kind of something beautiful, which should always be seen at this point in your first course in calculus, but it's just a little bit too advanced to usually cover in that course. So this is kind of the capstone where you kind of see what it was all for. And this is done by Newton. Newton was one of the inventors of calculus in the 17th century, and he was already sophisticated enough to be able to do that sort of mathematics. So really, in that first course of calculus, 300 years later, we ought to be able to do that too. I'm gonna then develop a little bit more trigonometry. I'll talk about Pythagorean triples and just kind of honing our skills in integration and differentiation and trig. After that, I'll start talking about hyperbolic functions, which is another topic which gets taught in kind of more advanced first calculus courses, but it's certainly not in AP calculus. So it's probably something that you haven't seen, and I'll talk a little bit about that in the context of the catenary. So that's a little bit more physics, a little bit more differential equations, those basic tools that everything is all about. In week 7, I'll start talking about Taylor series. That's something that you've definitely seen in that first course in calculus, and I'll use Taylor series to give the rigorous mathematical definitions of the classical functions, things like the trig functions, exponential and log functions. So I'm going to use those functions in the first 6 weeks quite happily, because I think we all have a fairly good, fairly intuitive understanding of what they are and what their properties are. Only in week 7 will I try to give you a rigorous definition of exactly what those functions are, because that's a little bit harder, and the right way really to do it is using Taylor series. I'm going to talk a little about polynomials, in particular cubics. I'll show you the formula for solving a cubic. I'm sure you all know the quadratic formula, but the cubic formula is quite fun. And that leads naturally to complex numbers. In fact, this is a much more classical topic than calculus. The formula for solving cubics, it was already rather well known in the 16th century, and that formula rests essentially on complex numbers. So they were already in place and being used, maybe not quite rigorously, but implicitly in mathematics. That was quite a lot before calculus. I will talk about the fundamental theorem of algebra, and then I'll go on and talk a little bit about complex power series and the very famous Euler's identity, which I expect you've seen. That's that identity, e to the I pi equals -1. In week 9, let me see, I need a little bit more room to give you my list of 10 weeks. This won't be exactly how it's timed, but this is the order of topics, roughly 10 weeks. So in week 9, I'm going to start talking about some of the mathematics that came after Newton and Leibniz and Taylor, all of that stuff. I'm going to start talking about the Bernoullis, and actually the Bernoullis was a little bit before Taylor, but right after Newton and Leibniz. I'm going to talk about Bernoulli's what's called the Brachistochrone. There's another lovely classical application of calculus involving differential equations and all the ideas that we've seen. And then I'll talk about another piece of mathematics of Bernoulli, which is the, I always spell Bernoulli wrong. Let me see if I can spell Bernoulli right. Bernoulli, there we go. All right, Bernoulli. I'll talk about Bernoulli numbers, and then that leads into kind of the final topic, where I'll start talking a little bit more about some of Euler's work. Euler was Bernoulli's student and really understood what was going on at that point, and did so many things. But I'll show you one more little piece of Euler's genius, and we'll talk about Euler's formula for the sum of 1 over n squared, and that should tie lots of those later topics together nicely. So that's my rough plan, my rough list of topics. I must say all of these topics are total old chestnuts. I think if you asked 100 mathematicians to give you a list of topics that should be taught in a history and applications of calculus class, I think 95% of them would list exactly those topics. So there are no big surprises here, but nevertheless, none of these topics are taught in most first courses in calculus, just because there isn't really time. And frankly, they all should be, because they're all so beautiful, they're all so brilliant, and every budding mathematician should know all of these things and have seen them and appreciate them. So that's kind of my goal. As we go, I'm going to talk about some of the history behind this. In fact, the history mania is going to be through readings, so I'm going to set readings each week, and from those readings, you'll pick up on the history. I'll just say a few things every now and then about the history. I'm not really a historian of this stuff, but I think you'll get a good sense of how this developed classically, and then in the late 17th, early 18th century. So all of this goes along with my webpage, which at the moment is here. So if you go to this URL, History and Applications of Calculus, there I'll post the readings, and I'll also post each week. I'll post, mostly they're already there. I'll post the homework problems for the week, and so the idea is that you watch the 3 lectures for the week, you do the recommended reading, and then you try working on the homework set. So on that webpage, you'll be able to download them as a PDF and try them. Once you've solved them, I'm really strongly encouraging you then try to type them up properly as a nice typed piece of mathematics, and to do that, you want to use the typesetting language called LaTeX, which is very professional and very fancy and very brilliant. So it's a great opportunity to learn how to use that. So actually the recommended way to do the homework is to download the template for the homework each week, which I'll write up, so that's a LaTeX source file which contains all the questions, and it also contains some hints, and then you'll just edit that file with your homework solution. So that experience is the idea is so that you learn how to use LaTeX, which is the right way of writing mathematics, and hopefully that should give you a little bit to focus on to keep you interested in solving those homework problems. They're not, as I said earlier, they're not going to be a lot of questions, but they should be interesting ones which are well worth attempting. So that's the plan. There's 10 weeks. Those are the topics. Each week there's also reading, and each week there's also a homework set, and I'm encouraging you to typeset that homework set using the LaTeX typesetting language. So all I want to do now is just quickly give a demonstration of how to use LaTeX if you've never used it before. So I'm recommending that you use an online server called Overleaf for doing LaTeX. So that's easy. You don't have to install anything on your computer. You just run it from a web browser. You can get more fancy, and if you have a laptop, you can actually download an installation of LaTeX on your computer, and it's a little bit faster that way, but I'll let you work that out. Overleaf is quick and easy. You can create a free account and get going very quickly using LaTeX to typeset mathematics. So that's what I'm going to do. I'm going to switch over to showing you how to do that right now. So what I need to do is, first of all, I need to go to my website. So let's go. So here's my home page. I'm going to go to the link that I gave you. So that's the History and Applications of Calculus page. You can see it's still a little bit under construction. I've only put in the material for week 1 on here. But in the next few weeks, I'll be adding all the material and posting all the other lectures to YouTube. So what I'm going to do is I'm going to go and click on the LaTeX template for homework solutions here. And I'm going to download that. So then I should have downloaded that to my downloads folder. I'm doing this all on an iPad, which is a little bit awkward. And then let me go into overleaf.com. So let's just type that in from scratch so that you see the web address to go to, overleaf.com. And the first time you go there, you'll have to create an account. I already have an account on Overleaf, so here it is. And then you open up your account, and you'll just want to create a new project. I'm going to create a new blank project, which I'm going to call History and Applications of Calculus. Let's create that. And it creates that new project, and it opens it up. It actually gives me a blank LaTeX file from which you can type stuff and then typeset. So there it is. It's giving me this file called main.txt, which is very simple and empty. If I were to click PDF here, and there it is, it's compiled that. So that's what that file produces. If I unclick PDF, you go back, that's the source. But we don't want to do that, so I'm going to delete that file. And then I'm going to click on this button in the top left here, this upload button. There we go. And I'm going to upload the file I just downloaded. So I'm going to browse my files. So let's see, I've got to go to the file system. I downloaded it using Firefox. So there it is. There's that template that I downloaded. And I'm just uploading that back to Overleaf. So there it is. It's now appeared, HAC on the left-hand side there, HAC Homework 1 template. If I click on that, there we go. It's now opened that file. So that's the template that I just got from my web page. And let's compile that. So I'll click on PDF. I've got to recompile so that it compiles that new text file. And there it is. Okay, so here's the file that you should get. History of Applications of Calculus Homework 1, Charlie Brown. And I just typed in a few random bits of LaTeX code for you to play around with at the beginning there. You see that just shows you some of the things you can do with LaTeX. You can create nice sigmas and integrals and all of that stuff. And then here are the problems starting at the bottom from question 1. And you see in this template, not only have I given you the problems, I've given you some hints for how to solve the problems. So if you attempt the homework from this template, you'll be able to see the hints. Okay, so and look at there's some graphs. I've written LaTeX code to draw a parabola there, and so there's only 4 problems on this homework set. Let me unclick PDF and go back to the source, and you can look at it. So any LaTeX source starts with a preamble, which is this first half of this page, and then you see on line 16 it goes begin document. So that's the end of the preamble, and in there that's the actual source that was producing that. You see there was the title, line 21, History and Applications of Calculus. Here were the sample lines of LaTeX. So you should just play around with this, edit them a little bit, and when you finish playing around, what you should first of all you should change that name, because that's you when you're turning in your homework, which of course you're not going to do because this is a self-study course, but nevertheless. So there we go. I've edited the name, and I'm not called Nonathan. Let me get my name right. There we go. And then you could recompile. Click recompile. So Charlie Brown is now Jonathan Brunden. That's better. And so once you've done that, then of course you would play around with this stuff. You see some of it looks quite complicated, but you just experiment, trial and error, copying other people's text source is the way to learn LaTeX. Once you've played with that, just delete all of that stuff. And then start working on the problems. Look where I've put hints down here. You see on line 85, there's hints. /M puts it in italics. You would change that word hints to solution. And then where I've written these hints, you would be editing that and typing in your solution to the problem there. There's problem 2. Problem 3, and you see this problem 3 was the one that had that graph of the parabola. So on line 139 here, I use something called TIX, which is a special language for drawing pictures in LaTeX, which is a little bit complicated. You see on line 141, that's plotting the parabola, the graph y equals x squared. You see the x star x, that's x squared there. And once you've edited stuff, then you just recompile it, and you're good to go. If you want to download the source, you just click on the menu here, and you can download the final PDF being produced. Okay, so I think that's all you need to know. I've gone back to my root page on Overleaf. I'm going to delete the new project that I just created because I don't need it. So I'm deleting HAC now, tidying up. And I think that's all you need to know. So the beautiful thing about using LaTeX is that it's trial and error. It's a little bit awkward. It's not as convenient as something like Microsoft Word because it's source, and then you have to compile it into a PDF and view it as a PDF. But it creates beautiful mathematics, and it looks very good. It makes most decisions for you, honestly. And whenever you don't know how to do something, all you do is you Google it. If you want to do something on LaTeX, you just Google LaTeX, how to draw a parabola, or LaTeX, what's the LaTeX for integral? And so many people use this that this will instantly pull you up something. There's also pretty good help in Overleaf. If you click on help in Overleaf and on their documentation, that's also a very good way of finding all those secret LaTeX commands. So that's another way to go. But really, the best way is to copy someone else's text source, which is why I've provided you with those templates for the homeworks. So that's all I've got for you today. So you're all set. You know how to proceed. I really urge you to devote yourself to taking this course. Don't try and do it too quickly. Take 10 weeks over it. Spend 1 week on each set of 3 lectures. That's the way your brain absorbs math the best. If you try and kind of cram all of it in a very short time, it'll simply go in and out, and you won't retain it. You have to look at it slowly. You have to go to sleep. Your brain will process it while you're sleeping, and then the next day you look at the next lecture. You do the reading, that'll consolidate it. You do the homework, you type the homework in using LaTeX. All of that is designed to get you to really know this material really well. So go at the pace of the course, take 10 weeks, and enjoy.